Next, we'll take a quick tour of the airflow demonstration unit before we get into the actual detail and data collection at each test section. Please bear with me. I'm going to have to carry the camera by hand, but this is just a quick tour, and you will see each test section in more detail when we start recording the data. The airflow demonstration unit is a forcing or pressurized airway, so it is like a bag line network that we studied earlier in the semester, if you remember that. Whereas the friction factor wind tunnel that we studied in our last lab session was a suction system. The anemometer calibration wind tunnel that we used in the very first lab session was also a suction system. Usually the airflow in a suction system is cleaner than the airflow in a forcing or pressurized system, and this will be something to keep in mind when you are doing the analyses for this lab. Okay, so now we'll take a quick look here, and again, bear with me. Okay, here is the centrifugal blower, which supplies the pressure. It's a 1 horsepower motor which spins at 3450 RPM, a pretty good clip. Here is the inlet with a bell, which we'll actually talk about a little bit later on. The squirrel cage is in here, discharges here, and it sends the pressurized air down the long rectangular duct. So the first test section that we will be using is right here, and this is a pitot tube traverse. So we have a small pitot tube, and we can move it sideways and up and down within the airway. And we have a set of marks engraved here, and we're going to take velocity pressure readings at specified locations in the airway. And you will, there we go. You're going to calculate the velocities from those velocity pressures. You'll take a look at the uniformity or non-uniformity of the distribution. And then also we'll take an average velocity for the whole airway, and we'll calculate a correction factor that we will apply to just the centerline velocity. And we're going to use that for the rest of the exercises throughout the lab session. Then we've also got some angled marks, which you can see right here. And we're just going to use those to study the effect of misalignment on the velocity pressure readings. Okay, the next test section that we're going to use is this plexiglass frame here, and we call this the flow regulator station. So we have a blank plug here, and then we can insert a variety of different sizes of plexiglass panels into the frame. So here's a fairly large size, and then it goes down to fairly small sizes. So with this test section, we're actually going to do 2 exercises. The first one is that we're going to use the plexiglass panels simply to restrict the flow in the airway. And then we're going to study downstream from the airway, so we're not going to change anything, but we're going to study the relationship of P equals RQ squared. Okay, so we're not going to actually use the area of the flow regulators, we're just studying the effect downstream of different Q's on the pressure drop. The second exercise we're going to do is to actually look at the shock loss across the regulator station. So remember, shock loss occurs whenever airflow changes direction. For example, with the larger size of regulator opening, there's not going to be a lot of obstruction, probably not a lot of shock loss, whereas with the smallest panel, there's going to be quite a bit of obstruction and therefore quite a bit of shock loss. Okay, moving down. The next test section is this plexiglass duct here, and we're going to swap this out for one of the steel ducts, and we call this the expansion and contraction test section. So we'll first have it oriented in this direction. Flow will come in here, so this is the original size duct. It's going to undergo a gradual contraction. It'll flow through this constant size smaller duct, and then at the discharge end in this orientation we have a sudden expansion from this opening back into the original duct. Then we're going to swap this 180 degrees so the air will enter from the original duct. It's going to experience a sudden contraction. It will flow through the smaller duct here, and then it will go through a gradual expansion back to the original size duct. So again, the concept of air flow changing, resulting in shock loss. We can study 4 different types of shock loss with this one test section. And continuing further downstream, we have a second pitot tube traverse station. We're not going to use that in this lab. And at this end, I just want to show you this collection of bend assemblies. We're not going to use these, but you see we have a good selection of right angle and curved bends. And as you can probably appreciate by this point, even though we haven't taken any data yet, a smaller, a rounded bend is going to result in less shock loss than a sharp bend. Now this has been codified. There's lots of tables and empirical relationships for this, and that stuff works pretty well, so we don't see it necessary to study that in the lab. You will cover that in lecture if you haven't already. Past the end here, the airway transitions to a vertical orientation and then heads back horizontally in the opposite direction, and we change the shape from a rectangular duct to a round duct. And up here is the discharge, and you can see a pitot tube right there at the discharge end, pretty close to it. And at this test section, we're going to study what happens when we use these flared conical shapes at the end of the airway. These are called évasés, which is the French word for flare. And you might think that the discharge of a duct of an airway is that. The air is exiting and that's that. But it actually turns out that if you use an évasé, you're actually guiding the air as the flow area is increasing, and you're reducing the shock loss of the air mixing at high velocities with the air in the local environment. And you can actually dramatically improve the performance of an airway with an évasé. So that will be the last exercise that we'll study. And thank you. Next one will be to take a look at the handout for the lab.